You hear us, Diane?
Yeah, we can hear you.
Okay.
Are you there, Diana? Maybe. Good. Good afternoon, Ocean Studies. It's my great pleasure to introduce our speaker today. We have Dr. Diana Townsend, who's zooming in this afternoon, and she is a quantitative ecologist. She is one of us. She graduated in 2014 from Ocean Studies with a bachelor's in marine biology, and she also minored in math. And she recently received her PhD from Northeastern University in ecology, evolution, and marine biology. Her research focuses on the intersection between mathematics and ecology, and specifically, she uses a combination of statistics and dynamical models to study the effects of dispersal and environmental heterogeneity on the synchrony of intertidal populations across scales. And the title of her talk today is Disentangling the Drivers of Spatiotemporal Dynamics in Trophic Metacommunities. So thank you so much, Diana.
We're not here.
To MMA. It's been a while. So today I'll be talking about some of the work that I did in grad school. And I'm sure most of you can recognize this picture here of Castine, which was one of my field sites for some of the intertidal studies that I did in grad school. But today I'm not going to really be talking too much about that work, and I'm going to be focusing more on the Okay. Did you not hear any of that? Okay. You can hear me now, though? Okay. Sorry, everybody. All right. So I'm happy to be back to MMA, even remotely. So it's good to be here again. It's been quite a few years. So today I'm going to be talking about some of the work that I did in grad school. And I'm sure most of you can recognize this picture as Castine, which was one of my field sites for some of the intertidal studies I did in grad school. However, I won't be talking much about that work today. I'll be focusing more on the theoretical ecology side of my work. And by theoretical ecology, I just mean the use of mathematical models, computer simulations, and stuff of that nature to understand different ecological concepts. In academia, especially in theoretical ecology, we like to use a lot of complicated words to say what we're trying to convey. And let's see. In layman's terms, my wordy title just means that I used math to help me understand the complexity of the natural world. Because the natural world is really complex. All of ecology is very complex. So sometimes we need different tools to kind of simplify all that complexity. So identifying the processes that drive community dynamics has been kind of one of the central goals of ecology. And this was kind of the baseline question that drove a lot of my research. And so before I get into my research or my methods or anything, I'm going to begin by talking about some keywords and concepts that you might not have necessarily heard yet in your careers in the marine sciences. So just so everyone's on an even playing field. So I'll start with metapopulations. Of course, a population is a group of individuals all from the same species, but a metapopulation, on the other hand, consists of multiple populations. Meta meaning multiple. So multiple populations, all of the same species that are separated across space. So for example, if we have this kind of hypothetical bluefish community here, which has 3 separate populations, in a metapopulation, these populations would be connected via dispersal. And when I say dispersal, I mean that individuals can move from one population to another. So an individual from population A can go to population B, and so on and so forth. So these distinct populations can still interact, individuals can still reproduce, so they're not completely isolated. And then, as we like to do in ecology, we can scale up, look at it from a bigger scale. So now we're looking at a meta-community. And in this theoretical fish world that we might have 3 distinct communities now made up of different fish species, rather than just the one bluefish species. And again, these communities will be connected via dispersal of individuals moving between the communities. So this is just kind of a bigger scope in ecology versus just looking at populations. We're now looking at multiple communities and multiple species as well. And then finally, we zoom out to the biggest scale in ecology, and we have a meta-ecosystem. And now this system is considering environmental factors like weather, and not just the biotic factors like we were talking about for metapopulations and meta-communities. And these distinct ecosystems are again linked to each other, either by the movement of individuals, like we were talking about with the other 2 systems, meta-communities and metapopulations. You can have the movement of individuals between ecosystems, or this time we can have the movement of abiotic materials like nutrients or sediments. And of course, this is kind of the biggest scale we can look at when we're talking about ecology, because we're considering all the abiotic factors, all the biotic factors, and their interactions as well. So as I mentioned, my goal was to look at the factors that drive community dynamics. So since I was looking at community dynamics, I decided to focus on meta-communities for my dissertation work. But instead of focusing on species that could voluntarily move from one community to another, I focused on some more familiar intertidal species like mussels or barnacles. And these species are different because they have a larval dispersal phase. So individual communities are connected by the movement of larvae of these organisms between the communities. So I wasn't looking at individuals voluntarily swimming from one community to another. I was looking at their larvae, which are kind of just moved by currents and things like that. So not really any specific voluntary movements. All right, so let's jump back to my question again and be a little more specific with it. And so what exactly do I mean by community dynamics? And generally, this means we're studying how and why communities are changing in size or structure over time. So if we're looking at 2 separate populations here, one in blue and one in red, their dynamics are simply just their abundances measured over time. So how many individuals are present at certain time points. And these dynamics can fluctuate. They can be more stable and not change, or they could be kind of all over the place and chaotic. But today I'm going to focus mostly on populations that are fluctuating over time, like these 2 graphs show. So what causes communities to change in size over time? Or what affects community dynamics? In the 20th century, there were 2 major viewpoints on this subject. The first being the Nicholson camp, which kind of attributed more biotic interactions like predation and dispersal to driving and affecting community dynamics. But on the other hand, there was this other camp that kind of emphasized the importance of the environment in structuring communities. So things like wave action, nutrient, the sun, everything like that. They thought this was what was really driving community dynamics. And the 2 sides, these 2 biotic kind of versus abiotic sides, contributed to this ongoing debate about what allows species to persist and to maintain this so-called balance of nature, where local interactions have generally been associated with maintaining this balance of nature and creating more stable dynamics like this plot here. we're looking at some community dynamics, this would be considered very stable because the abundances of this species aren't fluctuating or anything. And so the first camp kind of assumed that ecological processes like predation and all those things led to more stable dynamics. While the other group was like, no, yes, that's true, but the environment is what's kind of perturbing populations and making their dynamics much more chaotic or unpredictable. So the environment's more unpredictable, and ecological interactions is a lot more stable. But this guy named Robert May came in and showed that species interactions like predation could actually cause really complex dynamics. And he kind of upset this entire mindset that everyone had for a while. So he kind of put an end to that really simplistic assumption that the complexity could tell us what the driver was, where local interactions are stabilizing, the environment is destabilizing, but instead there are tons of factors that are going to drive these complicated or non-equilibrium dynamics. Lots of factors are going to cause populations to fluctuate really chaotically. And so in reality, as was pointed out even in the 30s by Eldon, communities are inherently complex. And this balance of nature paradigm is very fundamentally flawed, especially in the world of ecology. It's a lot more complicated than just categorizing things the way that they were doing. And this can be seen in a ton of populations in nature. For example, in feral sheep populations, I know it's random, but they're shown to be very chaotic and lots of factors are causing them to, their dynamics to fluctuate like that. And it's also been shown in intertidal mussel species. So observing this natural complexity, we need to kind of shift away from the focus of whether or not populations are fluctuating or not, and focus more on the drivers of these dynamics, you know? And all of this isn't super important on its own, but understanding dynamics is really important when we're thinking about conserving species or predicting changes in a community, especially these days. So trying to understand these underlying dynamics will help us in, you know, conserving species and predicting where they're going to go in the future. So how do we do this? How do we look more deeply into community dynamics? And there are a lot of different tools for this, but the one that I focused on mostly was Synchrony. And Synchrony provides a great framework for studying fluctuations in nature. And Synchrony was first discovered or categorized by a Dutch physicist in the 1600s named Christian Huygens. And he noticed an odd sympathy, as he put it, of two pendulum clocks in his house. So he's the first person to really, you know, notice, or, you know, I'm sure he's not the first person to notice, but the first person to write about it and, you know, question why this was happening. And since then, synchrony has been characterized across individuals throughout nature, from the schooling of fish to the emergence of cicadas. There's tons of examples of synchrony in nature. And so it's a very common phenomenon. So synchrony can be extended across space as well to measure the correlation between different fluctuating populations. So say again, we have these two populations, one in red, one in blue, that are in completely different locations. They can still be synchronized across space, even though they're completely separated. So this brought up a whole new kind of scale of looking at things, not just looking at individuals who synchronize, like schooling fish, but populations that synchronize across space. So two populations are synchronized if they're fluctuating together, like these two populations here. They go up together, they go down together, so they're synchronized. And then they're asynchronous if they're not fluctuating together, if they're not peaking, if they're not troughing together. These populations would be considered asynchronous across space. And spatial synchrony is also common in populations in nature. One of the really, really classic examples of this is lynx populations across different regions of Canada. This was characterized, I think in the 40s or something. This data was taken for decades and decades and decades. And in the 40s or 50s, someone really sat down and noticed this very rhythmic behavior and synchronized nature of these different lynx populations that are spread all the way across Canada, and yet they're still synchronized. So spatial synchrony is definitely a pretty common thing that occurs in nature. And since then, we've kind of honed in on a few processes that drive spatial synchrony, 3 in particular. So if we have a hypothetical meta-community here that's made up of barnacles and then some resource like a phytoplankton. And if we're looking at the dynamics of just the barnacles here, sorry, moving my little window. And so if these populations are fluctuating and they're asynchronous, you know, the barnacles in the red population and the blue population are separated in space, they're asynchronous. There are 3 things that can possibly synchronize their dynamics. Oops. And the first one being that, if this species, this barnacle species, is interacting with another species that is synchronized, this can synchronize their dynamics across space. So if these barnacles are preying on these phytoplankton and the phytoplankton are synchronized, this interaction can cause the barnacles to become synchronized across space as well. So trophic interactions with other correlated species can result in spatial synchrony. Additionally, if the environment that these species are experiencing are correlated, then this will synchronize the barnacle populations as well. So if these populations are experiencing some weather conditions or the same weather conditions that are synchronized, or synchronized fluctuations in runoff or something like that, that can promote synchrony in the barnacle populations. So interactions with other synchronized species or synchronized environments can really push populations into being synchronized. Even if they're separated by, you know, miles and miles apart, they can still become synchronized if they experience these different processes. And then finally, one of my favorite ones is dispersal. So if we talked about dispersal a little bit already, if we are experiencing dispersal between these 2 populations, this can promote synchrony because, you know, if we're sending a bunch of propagules from this location to this location, that can really synchronize these 2 populations across large spatial scales again. And I'm only going to be focusing on the first chapter of my dissertation today, which focused only on dispersal. But for my other chapters, I did focus on a combination of all of these traits. But today we'll just be talking about dispersal. And one more important point to note before we get into the actual research itself, if we're back to looking at these 2 populations in red and in blue, if the 2 populations are fluctuating together, both of them are here, you just can't see them. If they're fluctuating together, they are synchronous. Again, if they're not fluctuating together, if they're not peaking and troughing together, they're asynchronous. So this plot would have high synchrony, this one would have low. But synchrony is also important because it can be an indicator of how stable a population is. And generally, a more stable population is generally healthier. So that's why synchrony is a really important kind of indicator of a population's health. And so synchrony and stability are related. And the reason for that is, you know, if we're looking at this synchronized population, they're going to be at an increased risk of extinction if they experience a perturbation. And what I mean by that is, say these populations are fluctuating right here, and they experience some perturbation like a storm or something, which is signified here by the lightning bolt. Since both of these populations are fluctuating together, and if this storm or whatever hits when they're both, you know, on the downswing of their fluctuations, then both populations are likely going to go extinct. So synchrony is generally associated with low stability. This situation's unstable because, you know, something comes in, both these populations are on a downswing, they could both go extinct. So that's low stability. But on the other hand, if we have an asynchronous population where one's on the downswing, one's kind of on the upswing when a storm comes in, that might only knock out one of the populations. So the population can still persist, even though one of them got knocked out. So asynchrony is generally assumed to be better for populations that are separated across space. And we'll be talking a lot about this relationship today between synchrony and stability. So synchrony is generally bad and unstable or not stable. Asynchrony is generally a little better. All right, so with all that background, we can jump back into my research specifically. And as I mentioned, I wanted to look at the relationship between dispersal and synchrony and stability in metacommunities across space. So very wordy, but can be broken down and made a little more easy to digest. So yeah, the focus is dispersal and how that can affect synchrony and stability. And after this, of course, I'll talk about the implications of this. Of course, again, on its own, it's not the most important thing in the world, but it does have some big implications and can kind of give us more information on the best ways to conserve certain populations. All right, let's see. All right, so again, as I mentioned, we're just going to talk about dispersal. So we're not going to think about the environment. We're not going to think about species interactions. We're just going to think about how dispersal is a factor that drives synchrony. And I focused on dispersal because it's definitely an important process. And it's been characterized as kind of a double-edged sword, in that it can be a good thing, but it can also be a really bad thing. And it can be a good thing because it can bring communities back that are close to extinction. So if we have this kind of example theoretical community here that has this coastline here, and then we have two locations on it that's made up of barnacles. One site has a high number of barnacles, the other one has a low number of barnacles. The larger site can actually rescue the smaller population from extinction, which will eventually increase its abundance. So that's great. Dispersal can definitely be a good thing by rescuing populations that are close to extinction. So these are known as rescue effects. So this is definitely one of the major pluses of dispersal. It can definitely be a good thing. However, it is a double-edged sword because too much dispersal can be very detrimental. So if we get too many or too much dispersal from one site to another, that can result in the process that we talked about earlier, which is synchrony. And synchrony is not generally great because if the populations are doing the same thing, some perturbation comes in, wipes all the species out, then we're done. Then the species is extinct. So generally, high levels of dispersal are not considered a good thing in ecology. So too much dispersal can be destabilizing and can be a bad thing. So it's definitely a double-edged sword. Can be definitely good and prevent extinction, but can also be bad and promote extinction. So no winning here, depending on the level. And just to reiterate this relationship, because this is really important for the results of my studies, high levels of dispersal are definitely expected to promote synchrony. And I'll be coming back to this figure later on, but this is a really important figure because it kind of lays out how we look at synchrony or how we plot synchrony. So generally we plot dispersal on the x-axis of whatever plot we're making. And this will range from no dispersal, there's no movement, to a higher level of dispersal. And then we'll generally put synchrony on the y-axis. And that'll range from no synchrony to perfect synchrony. So we'll be coming back to this figure, but this is kind of the historical view on this relationship where dispersal promotes synchrony. And you can see where that double-edged sword is coming in. Low levels of dispersal are great. We're still having individuals being moved to other populations. We can rescue them, but too high, we become synchronized. And we talked about how detrimental that can be. All right, and again, it's not just dispersal and synchrony. Stability is also a big part of that, like I said. So when there's low synchrony, its stability is high. The populations are much more stable, less likely to go extinct. But once they become synchronized, stability drops right off, very unstable. So this is the historical relationship. This is what we expect to see based on previous studies and previous simulations. And even further than that, in historical studies, typically people implement dispersal as a very perfect and correlated process so that different species, so if we're back to our little meta community here, we have barnacles and mussels. In previous models, people would implement this so that both of these species disperse at the same time, they disperse the same amount, and they go to the same locations. So these two populations, these two species would disperse in the same exact way. So that's historically what we would do. And that's what's kind of led to this, this relationship between synchrony and stability. However, we know that's definitely not the case in the natural world. Species definitely have different dispersal abilities because they release propagules at different times. They have, some larvae have behavior in the water column, so they can, move up and down in the water column. So there's some behavior. So as in most cases, species, don't behave exactly the same way. So the previous way we were implementing dispersal was pretty unrealistic. So because of these two differences, or all the differences, there's a ton of different ways that species differ in their dispersal, but these are two of the major ones. But differences in dispersal can lead to differences in recruit time, or sorry, in destination, where populations recruit to. Again, they recruit different amounts. So of course, in nature, it's much more complicated than we've kind of viewed it in the past. So I definitely was interested in, if we make dispersal different among populations, what does that do to the overall community? So that was my major goal here. I wanted to see differences in recruitment and how that affects that, very accepted relationship that we had between dispersal, synchrony, and stability. Because again, as I mentioned, the natural world is much more complicated than that was portraying. And as I mentioned, I was using a meta community. I wanted to look at species that had a larval dispersal phase. And to do this, I used a bunch of mathematical models. I used computer simulations, and I did all of this in R. So I put the models in and had to, debug it and stuff. But it looks more complicated than it was. I'll be showing you my models in a second. But I simulated this meta community, and I simulated a bunch of different sites in the meta community, and each site had 4 species in it. The 4 species were this resource. The resource will always be in black. I had 2 competitors that ate the resource and competed for the resource. One was in blue and one was in green. And then I had this predator that ate these lower level competitors in red. So I had 4 species to focus on, and this is also known as a keystone food web. So each site in my meta community had this keystone food web. All right, and remember I'm focusing on dispersal, and to simulate that, I had individuals leave each site in their meta community at this equal rate. I kind of grouped together all of the consumers. So I considered consumers to be the predator and the 2 competitors. So all of those 3 species were kind of lumped together. And then the resource was kind of put into its own category. So all of these different individuals would emigrate away from their sites. So the 3 consumers would go together into this, general pool of individuals who left sites, and the resource went into its own kind of separate pool. So I didn't exactly keep track of where each individual went. I didn't pay attention to like, oh, individual 1 or this one individual went from site 1 to site 50. because that's more complicated than it needed to be. I didn't need to keep track of individuals. I just needed to know how many that I had. So that's why I used this kind of global pool thing and didn't keep track of which individual went to which site. That would be a lot more complicated than was necessary for this. Now, the fun part was the immigration that I did. Individuals were then sent back from the pool at different rates to each of the sites. This is the part that differs from classical studies, because this is how dispersal happens in nature. It's much more irregular process than we've thought of it before. And past models have usually implemented this as a much more uniform process. So on the next slide, I'm going to briefly show you the models that I used, but they're pretty intense. So you don't need to understand any of the parameters. I'm going to walk you through, the major parts of it, but I just want you to see what the exact equations look like and how we're able to do all this, because it's kind of easy to think about this in, a theoretical little community mindset, but it's actually equations that are making all of this happen. So again, the equations are not super important at all. Again, I set them up in R, had the computer run this hypothetical meta-community. But an important thing to note is that, as I've mentioned, ecology is very complicated. Everything's connected. So there's no way to really account for everything that could possibly influence a community. And so we use these models to kind of make our lives easier and to simplify these really complex systems. So we want to create the simplest possible model that we could that still reflects what's happening in the real world. So these look really complicated, but they could be much longer than they were. So, and these still do kind of reflect what's happening in the natural world. And that's our goal, to make them as short as possible while still being fairly realistic. All right, but the important thing to note here is that I had an equation for each of my species. Again, we had a predator, one consumer, and then a resource. And these equations are just tracking each species' abundance over time. So we're talking about community dynamics that are fluctuating over time. That's exactly what this model was doing for me. So that first term, if we look at the equation again, all those large first terms is just signifying predation, or each species consuming its prey. So predator 1 eating the consumers, and the consumers eating the resource. But the resource didn't have a predation term, it just had this general growth term, because it didn't have anything it was preying on, it was just growing, because it was the lowest level. And then the second term represents those kind of lower trophic levels being consumed by their predator. So each of these competitors being consumed by the predator, resource being consumed by these competitors. And that's why it's being subtracted, because being consumed by a predator would decrease their population size. So that was our second term. Our third term was just for the top consumers. It was just a mortality term. And the resource didn't have one of these because it was already kind of built into that growth term that it had. So this is just kind of a background mortality term that again is being subtracted because it would decrease population size. All right, we're almost there. We're almost through it. So next we had emigration, which we talked about. That is individuals leaving their sites and migrating to that big pool that I mentioned earlier. Nothing special there. But the fun part is the immigration term. That's the term that I really manipulated to answer my question. And again, this is leaving the global pool and entering back to the sites. So that's why it's being added, because this movement of individuals to a site would increase their population size. So again, this is the term I manipulated to represent differences in dispersal, because remember, that's our goal. Dispersal is very different amongst individuals and species. It's not a very uniform process. So this is where I manipulated that. Oops. And again, I separated the 3 consumers from the resource, and this is how I did it. The immigration term for these 3 guys was different than this guy down here. So that's how I really implemented those differences in dispersal that I wanted to see. And this could definitely have been done so it was different for each individual species, but I think the results probably would have been the same either way. So differences in dispersal, this is immigration. Again, more likely what's happening in the natural world. And to kind of clarify that part a little more, this is how I implemented dispersal or recruitment. Here's an example of it. Again, we have this theoretical coastline. We have a couple sites here. If the, in the case that recruitment was negatively correlated, meaning a site might receive a ton of consumers and only a few resources, or vice versa, just a few consumers and a ton of resources. This is where I implemented a negative correlation. So these 2 groups, these 2 pools act very differently, which again is more likely what's happening in nature. And this is just represented by a -1, meaning they're negatively correlated. One's high, one's low. And on the other hand, if recruitment was positively correlated, which again is the typical method most models use, a site would receive a ton of consumers and a ton of resources, or receive not a lot of either of those. So this is perfectly correlated. The consumers and the resource would be doing the same exact thing. Again, that's what we expect, but that's not reality in the natural world. So now I had R do its thing and ran the model, ran my equations. And when I had it run these equations, I simulated 100 sites in my meta community. So 100 distinct little sites that individuals are immigrating to. And then those correlation values that I talked about for dispersal, I had a range of those too. Again, from -1 being perfectly negatively correlated to a +1, which is the traditional method. So I wanted to see, how different correlations in recruitment could affect the community dynamics. And I also altered the rate of dispersal from 0, meaning no individuals are moving at all, to a maximum level of 0.5. And that just means all the individuals are moving. Every time the simulation ran, all the individuals are moving to a new site. So no movement to maximum movement. And I also set it up so that my populations would be fluctuating. As I said, I'm focusing on fluctuating dynamics across time. And this was important because I was studying synchrony. You can't exactly measure synchrony if a population is stagnant over time. And as I mentioned, I measured synchrony, and this value ranged from 0, meaning there's no synchrony, they're not peaking and troughing together, and then ranged to 1, which is they're completely doing the same thing, going up and down at the same time. And then the last thing that I calculated was instability, meaning how unstable a population is. And I know it's kind of confusing because I've been talking about stability this whole time, but like with most things I had to do, with most things in grad school, you have to kind of find a different method if something doesn't work. And instability was just much easier to calculate than stability. And so I looked at instability at the local scale at each individual site. And then I looked at it at the global scale across the entire meta community. And now to the results. Bear with me, there are quite a few graphs, but that's kind of the nature of theoretical work, unfortunately. But to orient you to this is kind of like the example that I showed you earlier, where we have dispersal rate on the x-axis from no movement to maximum movement. And then we have our synchrony on the y, from no synchrony to full synchrony. And then there's a line for every individual in my food web. So we have resource, competitors, predator. they're all there, but they all overlap and do the same thing, so it's not a big deal. And then I plotted 3 of those correlation levels in recruitment that I talked about, which tells you how correlated, again, the dispersal is between the consumers and the resource. So I had a negative correlation between them. Remember, they're doing completely different things, kind of an intermediate correlation, and then a perfect correlation where they're doing the same exact things. And I'm only showing these 3 because there was no effect of varying dispersal on synchrony for my meta community. It was the same across cross correlations, so it's not a big deal. We don't need the in-between numbers. So what's interesting to note, though, with my results is I got this kind of weird 3-phase relationship between dispersal and synchrony. And that's kind of odd compared to what we've seen in the past. In the past, we've just seen a phase of no synchrony, and then it's high synchrony. But mine was kind of weird, and it started out with high synchrony. And interestingly, it's high at low levels of dispersal, which doesn't make sense with what we've known from previous studies. But this is regardless of correlation in recruitment. So for each of these 3, we got the same exact result. We still had that weird peak in synchrony at the beginning. And this was because of the way I implemented my dispersal. If you remember, I made dispersal a very large scale global process where all of my individuals went into these huge pools rather than them going locally from site to site, like it's been done in previous models. So if we look at the dynamics during this phase, we can see why they're synchronized. The populations at this point, if we're looking at community dynamics with time on the X, abundance on the Y, you can see that all my populations are still fluctuating at this point. And if you remember, when I ran my models, I wanted them to have fluctuations. So this is kind of a remnant of me giving them fluctuations at the beginning. And at intermediate levels of dispersal, synchrony drops to 0. And this is what we would expect from past studies. So there's not enough dispersal to synchronize the entire community. So this is very normal and expected. And the reason this happened was because all of my species kind of hit this equilibrium. So they weren't able to become synchronized because they weren't fluctuating anymore. You can't really measure how populations are moving in unison if the abundances aren't changing. And so my global dispersal system kind of homogenized the whole system. And there are a few kind of mathematical reasons for why this happened, but I won't bore you with the details of that. But this region does follow previous studies. It is kind of what we would expect to see. And finally, the system eventually does synchronize at high levels of dispersal, like I mentioned earlier. Lots of dispersal generally synchronizes the system. But again, it's kind of weird and different from what we've seen previously. Got this weird 3-phase relationship versus a 2-phase relationship. And it's also interesting to note that since I used those global pools, a lot more dispersal was required to synchronize the system. Because you can see in past studies, needed 0.03-ish dispersal rate. And for mine, I needed a 0.25 dispersal rate. So when dispersal was at such a global scale, needed a lot higher rate of dispersal to actually synchronize the system. So that's just a minor difference, but overall, that's pretty big. You need a ton of dispersal this way. And at this point, they synchronized again because the populations began to fluctuate again. They're in unison. That's what we expect. So next I calculated instability, and my graphs are very similar to the synchrony graphs. Dispersal rate on the X and instability on the Y. And again, instability is kind of counterintuitive with high levels of instability, meaning the system's really unstable, low levels meaning it's actually really stable. And just like with synchrony, we had these kind of 3 distinct phases between instability and dispersal, where at low levels, instability is really high. Intermediate levels, the system was really stable. And this was consistent across our cross correlations. So these first two phases were the exact same across these three different phases. But what's important to note is that from about a rate of dispersal of about 0.3 onward, correlation in recruitment actually does affect the level of instability. So this is interesting. Before, cross correlations had no effect on synchrony, but it did affect instability. And so instability is increasing the higher you go in correlations. And this was because of the way that consumers and resources were dispersed in these situations, and I'll kind of tell you why that is. So for a negative correlation, like I said, sites are receiving a ton of consumers and few resources, or vice versa. And that kind of had a stabilizing effect on the system, which resulted in the instability being much lower. So it's much lower here when the consumers and the resources were not correlated. But on the other hand, when they were correlated, when a site would get a ton of consumers or and a ton of resources, or a few of both, this kind of overwhelmed the food web, and either getting these high or low inputs promoted out of control growth. The system kind of got out of control, and this promoted really high instability. And this shows, given past models who have done it like this is the only result that we would have gotten if we only did it, if we only had consumers and resources being correlated. So that could be very detrimental, if we did it the way that it appears in nature, we saw a very different result in instability. So it's very important to, look at the differential effects of dispersal on community dynamics. All right, so let's talk about why this is interesting. So synchrony and stability were coupled at low levels of dispersal. They were doing the same thing. They were consistent. They were the same all across correlations. And as well as intermediate levels, doing the same thing. The relationship is inverse as we expect. No synchrony is actually very stabilizing. But they actually become decoupled at high levels of dispersal, where differences in dispersal actually affect the stability, but they're not affecting the synchrony. So synchrony and stability become decoupled. No effects here, but there is an effect here. And normally we would expect synchrony and stability to go together. And in this case, they don't. So this is a very important result. So this is important because it shows, if we're more realistic with our dispersal, where species disperse differently, this decouples synchrony and stability, and that's not what we expected or knew to be true. And this probably extends to the natural world as well. Synchrony and stability probably aren't as correlated as we think they are, or as coupled as we think they are. So this shows that double-edged sword that we thought dispersal isn't always so cut and dry, and definitely doesn't show up in the same way, or show up as readily as we would expect, as we would have expected if all of the species dispersed the same way. And this is really important to note, especially these days with rapid global change happening. We need to know what these relationships are so we can understand how communities are going to change. So that's all well and good, but what are the applications of this? Because in the sciences, we always need to justify why we're doing the work that we're doing. We can't just do it, we have to justify it. And I hope I've kind of convinced you that balance of nature phenomenon's not easily understood, and natural systems are inherently complex. But theory is very useful for helping us kind of tease apart the drivers of these dynamics that are really difficult to quantify in the natural world. And simply understanding how communities operate is not sufficient anymore. We need to be able to apply this knowledge so we can manage communities. And so quickly, the effects these ecological and environmental processes, the effects of these processes can be applied to spatial management. a lot of these management strategies kind of aim to maintain the balance of nature, which is especially relevant these days, with climate change. And for example, one management strategy known as marine reserves, which is a common management strategy, which kind of prohibits the removal of species in certain areas. But the problem with this method is it often assumes populations reach equilibrium. But fisheries are very much experience non-equilibrium dynamics due to fishing pressure. Fishing pressure decreases the abundance of these populations, and that pressure also increases how variable the dynamics are. So this is kind of a double jeopardy, which really puts these populations at risk of going extinct. So fisheries are definitely more prone to non-equilibrium dynamics than a lot of these methods would have you assume. And beyond reserves, people have kind of started delineating these reserves into networks, which are just kind of little patches of these reserves throughout a region. And like in a meta community, this kind of promotes the movement of individuals between these different pockets. And that's proven useful. Higher connectivity means we can kind of restore these different populations in these different protected areas. However, as I mentioned, theory predicts that connectivity can be bad, too much can be detrimental by promoting synchrony and then increasing extinction risk. But hopefully I've convinced you with my work that, that's not necessarily the case. We don't have to be scared of synchrony because dispersal may actually prevent synchrony based on what I've shown here. And that's contrary to what we've expected in the past. And so differential dispersal may actually allow species to persist in systems that really are highly connected. And this may allow for them to persist more easily than we thought. And so synchrony might not necessarily be as detrimental as we would have assumed in previous models. So quickly, I wanted to just chat a little bit about grad school. This went longer than I expected it to, and offer some advice for grad school based on my experience. If any of you are interested in grad school, where to start? So obviously I graduated from MMA in 2014. I had no idea what I wanted to do. I knew that I liked math. I knew that I liked science, but had no idea. But one thing that really did set me apart when I was applying to jobs after undergrad was I took a MATLAB course while at MMA. So I suggest all of you, no matter what career field you're planning on going into, to take some programming class if you can. R is really common in the sciences these days because it's free and there's a lot of resources, and so that's what I used for my PhD. But I originally learned MATLAB, but that set me apart because after undergrad, I applied to be a research technician in a neuroscience lab. I had no neuroscience knowledge, but had the programming skills that they wanted. So that definitely set me apart. So your degree title doesn't necessarily kind of pigeonhole you. It's more the experiences and the skills you acquire. And you're all already lucky enough that you're getting so many different experiences where you are. You guys get to go out on boats all the time and do your own projects. So that's good, and put all that on your resume. As for grad school, I promise I didn't sit on the computer all day. I did still get to go out and do some intertidal surveys. So you can combine theoretical work with more applied work. So don't let my results and my methods all scare you. You can definitely combine it all. But quickly, advice for grad school that I have is think about funding. Funding's really important. A lot of people go into a lot of debt in grad school, but you don't have to. If you can find the right program, you can get paid to be there, actually. At least that was important to me. I didn't want to go into more debt after college. Location can be important. That's up to you. You can almost study anywhere that you want. I know people that study corals down in Panama. I mostly stayed in New England. And then make sure your potential advisor that you pick gives you clear expectations of what they expect from you. Because a lot of advisors expect a lot from students, and that's not clear at first, and that can cause a lot of issues. So that's my advice. You're all welcome to email me. I'll have Professor Mullen give you all my email if you have questions about grad school. But I do recommend it. It's the best time of my life. Met amazing people, went crazy places. And so I'll take questions now if anybody has any questions about grad school, my research, or anything like that.
Can you guys hear me? Oh, there you go. All right, so went away. You guys still hear me? Yes? No? We just have a time really for one question before the next group comes in here. So does somebody have a question for Diana in terms of her research or grad school in particular? Okay, Bree?
I actually have many, but I'll just pick the one I really want to know. So depending on or regarding like synchrony, does and like the whole idea with meta-communities and meta-populations, can that apply to like cosmopolitan species that are like found like just like everywhere, or because I'm not sure really on like what constitutes a meta-community and meta-population based on like distance for your research? Thank you.
That's definitely a tough one, and it actually can be applied to huge scales. We're learning with climate change, things are synchronized across the entire globe, so that can definitely be expanded. But yeah, the limits of the distance are tough, but they can be applied to any scale that you look at. I'm sorry that I went so over time. I talked too much. Sorry.
For being with us here this afternoon. So again, let's thank Diana for her seminar.